All right. Last thing we're talking about in this chapter is electrolysis. Electrolysis is a process in which we basically apply electrical energy to make a non-spontaneous process basically occur. So for example, if we have sodium chloride, again, you can pretty much heat the heck out of it and you will not get back its elemental form, if you will. You will not get back the sodium metal or the chlorine gas in a normal situation, but you can apply a sort of external battery and basically break apart these guys into chlorine and sodium coming out. So in this case, our anode is actually our chloride, because our chloride we're going to take back to chlorine gas, which means it is going from -1 to 0. That means if you follow our little number line thing, it is going in that direction and it's going through oxidation. So it is actually going to be our anode in this case, while we would be taking the sodium ion back to solid sodium, which would be going from +1 to 0, with, once again, if you follow that, would be going in this direction, going through reduction. So it is sort of the opposite, right? When we kind of put it together, it is the sodium that loses electrons, right, and gets oxidized. But in this case, we're kind of putting it back together the other way. So it is the sodium here that is getting reduced. So that is why it's on the cathode side. And that's what we see here. That way we end up back with our sort of elemental forms, if you will, of that ionic compound. Any questions on that there? Same thing could happen with water. You could take some water, add a little bit of acid to kind of help it along, and basically get a 9-volt battery with the proper electrodes, and you basically can do this. And it will basically break apart water, obviously, back into sort of its components of hydrogen and oxygen gas in this particular case. And that's what we see here in this picture and in a real life picture over here. We see the bubbling occurring, which is our hydrogen gas and our oxygen gas. And once again, in this case, it is the oxygen that is going through oxidation, as it is really going from -2 to 0, right? And again, going from -2 to 0 means it is going through oxidation. The water is really the hydrogen going from +1, if you will, to 0 in this case, going through reduction. So again, the opposite of sort of putting it together, breaking it back apart. It usually, like I said, does require some acid. So you got to add a little bit of acid there. So sometimes in electrolysis problems, they will not scream in bright lights that you are talking about the electrolysis of water. They will just say something about using sulfuric acid or dilute sulfuric acid or some type of acid. That usually indicates that we're talking about sort of the electrolysis of water that occurs. Obviously, our gas is in this empty spot. And why do we have more hydrogen than oxygen? Because it's H2O, right? So twice as much hydrogen and we get oxygen, right, in that little space there. So let's talk about sort of electrolysis problems. They sort of run in one of two ways. They oftentimes will give you the current or the amperage at which you are running a electrolysis cell for, and kind of how long you're going to be running it from or running it for. And that's where this relationship could come into place. A charge or a coulomb is equal to the current in amperage times time, which means a coulomb is equal to an amp times seconds, if you will, which means an amperage there is a coulomb over a second. So that is a way you could kind of convert the amperage they give you into coulombs per second. Obviously, the time in this case would need to be converted to seconds in most cases so that the units here cancel out correctly. So if they say they run it for like 3 hours, you probably need to convert that guy into seconds so everything cancels out. Once you do that, you typically will take your coulomb per second, you will times it by your seconds and time that you ran the cell for. That will give you basically a coulomb of charge. At that point, you can use Faraday's constant to do a conversion between coulombs and moles of electrons. And at this point, you will then have moles of electrons. This is where basically the two half reactions would come into play for the anode and the cathode side of your electrolysis cell. And in that, you would have at some point, some electrons and maybe, some type of metal here. You would do a mole to mole relationship between these guys from the half reaction. And that will take you from moles of electrons to moles of whatever you're interested in. At that point, you have really kind of two options usually in these type of problems. The first option is they want to know, for example, how many grams you may collect. So once you get the moles of the element you're looking at, you obviously can use the molar mass to convert it into how many grams that would be. Also, sometimes they're interested in how much volume of a gas you collect, like the hydrogen and the oxygen example. And since those are gases, we sometimes will need to use our good friend PV equals nRT, or the ideal gas law, where pressure, right, needs to be in units of atmospheres, volume needs to be in units of liters, temperature in Kelvin, obviously N should be moles, and the R here is actually our 0.08206 number there, liters times atmosphere, Kelvin, and mole. So sometimes in these electrolysis problems, you're collecting a gas, maybe chlorine gas, hydrogen gas, oxygen gas. So sometimes they're interested in how much volume you would collect. So sometimes you'll need to take the moles that you get at the end there and use the other information like the temperature and the pressure and stick it into the ideal gas law and solve for volume to figure out the volume of the gas that you would be collecting. Any questions on any of that there? All right, so let's take a look at one here. Actually, let's get that one. Let's take a look at this one first here. So how much calcium will be produced in an electrolysis cell of molten calcium chloride if a current of 0.452 amps is passed through a cell for 1.5 hours. So in this case, we're starting with calcium chloride, which basically means we have a calcium ion and a couple of chloride ions, right, that are happening here. And in this particular case, we're interested in the calcium. We're going to take the calcium back to solid calcium, which means my calcium here is going to be my anode or my cathode in this reaction. So it's going to go from +2 to 0. That is the cathode, right? That's going reduced. Yeah, that's being reduced. And really in this cell, it is the chlorides going to chlorine, right? Going from -1 to 0, which means it is being oxidized in this case. So remember, it's a little bit opposite of, how you put it together. We're sort of breaking it back apart. So the anode in this case should be our chloride, and the cathode here should be our calcium. Again, we're taking it from the ion form back to kind of their basic elemental form, sort of in each of these cases. Any questions on that there? All right, so now we could figure out, we're really interested in the calcium here. So we could start with the 0.452 amperage there. That is the same as 0.452 coulombs per second. I am going to run the cell for 1.5 hours. In 1 hour, there are like 3,600 seconds, I think. Yeah. So we could convert that into seconds at this point. So we take 1.5 times 3,600, gives us about 5,400 seconds at this point. So now that I have this, and the reason I needed to do this was so that the unit-wise, these two guys would cancel. So we want to make sure everybody's in the correct units. I can now really take the time I'm going to run the cell times the current at which I was running the cell for. So we'll take our 5,400 seconds, which is how long we're running the cell. We're going to take basically the amperage of the cell. The seconds will cancel. That will get us 0.452 2440.8, I think. And these would be coulombs. At this point, we would use Faraday's constant to go from coulombs to moles of electrons. So this is pretty standard first step on these type of problems, is these few steps right here. We're going to do our 96,500 coulombs per 1 mole of electron. So we're going to divide up by 96,500. Going to give us, we'll call it 0.025 moles of electrons. Any questions so far? So really, like I said, these kind of first steps here are fairly common in these type of problems as to what you kind of need to do. At this point, we really could go to either one of the things. If it, if we were interested in both, we could do both. But in this case, we'll do what the problem asks, which is we're interested in the calcium. So once we get to moles of electrons, we could use the balanced half reaction to go from moles of electrons to moles of calcium. And what we see from the half reaction is every 2 moles of electrons give us 1 mole of calcium. So we're going to use that really as a conversion factor. So that's going to give us 0.025 moles of electron, 2 moles of electron on the bottom, so they cancel, 1 mole of calcium up on top there. And that would get us that guy divided by 2. 0.013 moles of calcium. And if I want to know how many grams that would be, I'm going to use the molar mass of calcium, which is 4008, I think, give or take. Does that look right to somebody near a periodic table? 4008 grams per mole of calcium. So if I times that by 4008, gives me about 0.51 grams of calcium. About 0.5 gram of calcium would be produced in the cell if you let it run at that amperage for about 1.5 hours. Question on any of those steps there? If I was interested in chlorine, I would do the same basic start, except at this point, I would then go to the chlorine half reaction and do the moles of electrons to chlorine. And since chlorine's a gas, perhaps they would give me a temperature and some pressure, and I could go into the ideal gas law and figure out the volume, or I could also just figure out the grams of the chlorine that would be produced as well. Question on any of those there? All right, so why don't you try one, which is the one we skipped. We'll go back to it, which is the water example. So if we run a cell at 1.26 amps and we run it for 7.44 hours, how much volume of each gas will produce at STP? So we're going to run basically this cell for, what is it there? Well, 7.44 hours and 1.26 amperage, I believe. And we want to know the volume of oxygen gas and hydrogen gas at STP. STP is standard temperature and pressure. That's a pressure of what? 1 atmosphere and a temperature of 273, yeah. STP, yeah. I'll give you the reactions for you. And like I mentioned before, as you can see there in this question, it really doesn't necessarily mention water, but it just says sulfuric acid and stuff like that. So again, that is sort of how it's sort of talking about water. Look here and see what we got going on. So really, once again, we're given the amperage of the current for the cell. We have how far we're going to run it for, or how long we're going to run it for. So really, again, the start here is very similar to what we did before. We need to get our hours into seconds. So we're going to multiply by 3,600 seconds will get us there. So we're going to take 7.44 times a 3600, going to give us, looks like 26,784 seconds. Once again, our 1.26 amperage is the same as 1.26 coulombs per second, hence why we need to get this guy into seconds. So we're going to multiply those guys together. That's going to cancel out the seconds at that point, and we will end up with, looks like, calculator's hard to read, but I think it says 33,747.84 coulombs. At this point, this is where we're going to use Faraday's constant to really get us into moles of electrons, so we could then use our half reactions for each of it here. So we're going to take that number there, our 33,747.84, and there's a dot right there. Coulomb, we're going to divide by Faraday's constant, 96,500 per mole of electron. And if we do that there, looks like 0.350, we'll call it, moles of electron. Any questions so far on the first part here? Now, once we really get to moles of electrons, that's where we can use, obviously, the balanced half reactions to get us to each of the elements that we're interested in. In this case, we're actually interested in both of them, the hydrogen and the oxygen. So we'll carry that number over to the next page here where we have our half reactions to look at. And we can see that we have 0.350 moles of electrons. From the half reaction for oxygen, it is 1 mole of oxygen gives us 4 moles of electrons. So we could do that real quick here. 4 moles of electrons gives us 1 mole of O2. So if we take that guy, do a little dividing by 4, gets us 0.0874 moles of oxygen. We would obviously want to do the exact same thing here for our hydrogen. Looking at our hydrogen, that is, if we multiply the 4 in, that is 4 moles of oxygen, 4 moles of electrons to 2 moles of hydrogen. So 4 moles of electrons to 2 moles of hydrogen. Or you could do 1/2 as well. Obviously, that's the same thing. And if you do that, gives us 0.175 moles of hydrogen. Any questions on either of those there? And again, you can reduce that down to a 1-to-2 relationship if you like as well. At this point, we should probably go into our ideal gas law since we are looking for a volume. And now that we have moles for each of those, and obviously we always have R, so we could do PV equals nRT. We'll do it for the oxygen here. And if we solve for the volume, it would be nRT divided by P. That would be our 0.0874. Our 0.08206 liters atmosphere Kelvin mole, and our temperature of 273. I'll go high so I don't get in that way of that thing. I'll just move it. 273 Kelvin, all divided by our pressure, which would be 1 atmosphere in this case. And I'm just gonna up there a little bit. 273 Kelvin. All right, everything's going to cancel out here, obviously, except for liters, and that will get us the volume of oxygen gas at SCP being like 1.96 liters, give or take, of oxygen. We could also obviously do the same thing here for hydrogen. Everything will be the same except that we will have a different moles, which would be 0.175. 0.08206. Our 273 Kelvin, all once again divided by 1 atmosphere. And for our hydrogen, then looks like 0.175 times 0.08206 times 273 gets us about a 3.92 liters of hydrogen would be collected in this case. And that is about a 2-to-4 ratio there of gases, right? Twice as much hydrogen as our oxygen. First off, any questions on those calculations? Could I have solved it a different way? I could have, if you remember this relationship, that since we were at STP, 1 mole of any gas equals 22.414 liters. So you could have just took the moles of either one, really, 0.175 moles, and times it by 22.414 liters. And should pretty much give you that number as well. So you could use that relationship, that is because it's at STP. That's the only time you can use that relationship, by the way, right, is at STP. Otherwise, you could clearly just stick it into the ideal gas law and not a problem. Question on electrolysis problems. Variation of this problem would be like they tell you how much you collected. Yes, you go backwards, maybe figure out how long you ran the cell for or how much amperage you did, which is basically just the opposite direction, heading backwards. Any questions on any of that there? All right, that wraps up this chapter here. We will get a little bit into the next one. So just give me a second here to punch it up. All right, so the next chapter we're going to talk about is nuclear chemistry. I think it's 21. It might be 20. I think it's 21. It's 20-ish, I know for sure. So in this chapter, obviously, we're going to talk about nuclear chemistry and balancing nuclear reactions and some kinetics that involves nuclear chemistry. So let's talk a little bit about radioactivity. Radioactive nuclei spontaneously decompose into smaller nuclei. That is basically radioactive decay. If something does go through that, obviously it is unstable. Typically, wherever it starts from, if it does decay, the original guy is sometimes referred to as the parent. And the one that is formed as sort of a result of that decay process is what is referred to as the daughter nuclei. Nuclei is like the nucleus we sort of talk about. Any nuclei that have 84 or more protons are radioactive, which is for the most part your bottom part there on the periodic table. The real bottom row there is all those guys are kind of radioactive. There are different types of radioactive particles that we do come across, and some symbols that we do see in nuclear chemistry. Our good friend Rutherford, do you remember him? He did some experiments with some gold foil, right, and all that good stuff. Discovered sort of 3 types of rays. There are alpha rays. Alpha rays or alpha particles have basically a kind of +2 charge there and basically a mass number of 4. It is really the helium nucleus. So alpha particles in nuclear chemistry is sometimes abbreviated with the alpha symbol, or sometimes just helium is used to represent an alpha particle. So those are 2 common ones that are used there. A beta is kind of like an electron, and it also has a couple of symbols that are commonly used, like the beta there are really the electron. The gamma ray is just pure energy, so sometimes just like that. You might remember gamma rays from when you looked at electromagnetic spectrum, and it was pretty much past X-rays, has very short wavelength, right? So short wavelength means very high energy. It means you should not be just standing there and letting it hit you all day. Yes, it's just really, really pure energy. In addition, there are some other symbols that will come across very commonly in here. Sometimes unstable nuclei will emit what is known as a positron. It's like an electron with a better attitude. Thank you. I'm here twice weekly. So it is actually the symbol for a positron is pretty much the same symbols here, except that it is +1 that they use there. So they will use similar symbols for those guys, sort of a positively charged electron. Occasionally, there will be reactions where an electron capture will occur. Electron capture is pretty much what it sounds like. An electron on the reactant side basically gets bombarded into something, it hits something, and it reacts with it. So that brings us to our good symbols that we oftentimes see a lot of in nuclear chemistry. Top number is our mass number, right? Mass number is the number of protons and neutrons in an element. Bottom number there left is our atomic number, which is the number of protons in a nucleus. Can you find both numbers on the periodic table? No. You could only find the atomic number on the periodic table. That is the number above the symbol. The number on the bottom is the atomic mass, not the mass number. If you want to calculate the mass number, atomic number, number of protons, electrons, or neutrons, they are all positive whole numbers. So good way to remember it is they have to be whole numbers. If you look on the periodic table, clearly most of the atomic masses are not whole numbers. Oftentimes people get confused by that because the mass number and the atomic mass are similar type of number in terms sometimes, but they are not found in the periodic table. Only the atomic number is. And here are some other sort of symbols that we very much come across here in nuclear chemistry. Some of these we just went over, but let's take a look. A proton is sometimes used, and it is also sometimes used two different ways to represent a proton. P for proton with a mass number of 1 and atomic number of 1, and hydrogen, which is also sometimes referred to as a proton, 1 proton and 1 as well. A neutron is also another very common particle we see a lot in nuclear chemistry, and that is the symbol for it, mass number 1, atomic number 0. By the way, to find the number of neutrons, you do what with those two numbers? You subtract the mass number from the atomic number, right? If you take the mass number minus the atomic number, that does give you the number of neutrons. Here is our electron, our beta particle. And again, you can see it is basically kind of the same symbol as we see for our positron, which is a positive electron. And here's our two common symbols used for our alpha particles. Again, is wrong with the mass number and the atomic number that is there. So these sort of symbols you should be familiar with, and obviously the charges that go with them, because it's going to be really important in terms of balancing the nuclear equations to sort of figure out those numbers and know what those are. Any questions on that there? Yes, sir. How do you determine? We'll talk a little bit about it when we balance equations, but for our purposes, that's how you would figure it out based on sort of the balance equation and you know what you need to do that. Now, different sort of particles do penetrate, for example, lead further than others. So alpha particles only go 0.01. Beta particles penetrate a little bit further, and gamma particles keep going and stuff like that. So, you know, if you ever find yourself working with radioactive material, you should always figure out what type of emitter it is and make sure that you use the proper sort of protection. Sometimes you just need gloves and a coat. Sometimes you need a lot of lead and like concrete behind you, between you and the radioactive device. So it's always good to figure out what type of emitter it is and make sure that you are using the proper sort of protection. Sometimes, you know, people forget to mention these good things to you as you're working in places. Again, here's just some of those symbols that we see. Now, if you see just a beta written like that and nothing else written, it's probably pretty safe to assume that it is the beta particle. If it is like the positron or something like that, they typically will put something with a positive on there. So, you know, they'll sometimes put like just the plus up there and they'll tell you, hey, it's the positron one. So again, if you just kind of see the beta particle with nothing, it's probably safe to assume it is the beta particle and sort of the negative version of it. All right, nuclear equations and balancing nuclear equations is like super hard. Not really. It's really just adding. So when we balance a nuclear equation, there's really kind of two things that need to be balanced, a little bit different than a traditional equation. And that is pretty much when you add up all the mass numbers, which a reminder is the number that is up on top is the mass number. The atomic number is the number that's on the bottom. Mass number is obviously our protons plus neutrons, right? Atomic number is our protons here. And when we add up all the mass numbers on the left-hand side here, they need to equal all the mass numbers that you add up here on the right-hand side. So here we have 235 and 1, which gives you like a 236 there on the right-hand side, or left-hand side. On the right-hand side, we got 138 plus 96, and we would also multiply 2 times 1 there on top, and that would give us 2 more. Which would give us 236 there on the right-hand side. On the other thing that needs to be balanced is the atomic number. So the number of protons there. And it's the same deal on the left-hand side is what we're looking for on the bottom. So in this particular example here, that is a 92. And adding up all of the atomic numbers on the right hand side gives us 92 as well. So to have a balanced nuclear equation, that's pretty much all you need to do is make sure all the mass numbers on the left equals the right and all the atomic numbers on the left equals the ones on the right. So how would something like this go? Well, one way is something could be missing from this equation. So for example, if we took out, say, this guy right here, and we weren't sure, you know, what that was, we can look back at this and basically add up the bottom number, as that is going to be what's going to tell us what element or particle is missing. So on the left-hand side, we have 92. If we add up everybody but the guy box, that's 55, and 0 gives us a 55. So basically, if we subtract those two numbers, that is going to give us a 37, which is the missing atomic number that we see there. We would then go to the periodic table, which is our other good friend when we're doing these type of equations, and we would look up number 37 there, and we would see the symbol RB, and that is, again, how we get to that guy that would be in the missing box. To finish out the top number, we would do the same thing. So before we had 236. Without the middle guy there, we basically had 138 plus 2, which is, again, from here, you got to multiply those two together, gives us a $1.40 there. Once again, if we subtract the 140 from the 236, that is going to leave us the 96, where our missing sort of mass number would come from. So that is one way these sort of problems are, something sort of missing in the equation. And really the good approach is to go with the atomic number, because in most cases it will match somebody on the periodic table. It is potentially possible that the missing thing is one of those particles, so maybe a hydrogen, which would still match, an alpha particle, which would probably still match as well. But, you know, you could have a neutron, you could have some other type of particle that's missing. But probably 9 times out of 10, you could go to the periodic table and find sort of the element that's missing. And then you want to finish out by figuring out your missing mass number. Now, the other way is you'll sometimes just be given things sort of in words, if you will, and they'll say, hey, this guy goes through alpha decay or beta decay or something like that. So they'll sometimes say, hey, it goes through alpha decay or any of those other particles. And what that essentially means is, in terms of the arrow, that is where it will end up, will be on the product side. So if anything goes through any type of decay, they will typically tell you what type of decay, like alpha decay, beta decay, positron emission, something like that. those particles will end up on the right-hand side. Your original guy will end up on the left-hand side, and then you could proceed to figure out what the new isotope would be on the other side. A couple other words. So anything that is going through decay, anything that is emitted, those particles always end up on the product side. Anything that is bombarded, anything like an electron capture, those particles end up on the reactant side. So those are the common sort of verbiage that you sometimes see in these problems. Bombarded, electron capture, that's going to put that particle on the left-hand side. The reactant side, anything that goes through some type of decay, emits some type of particle, that particle ends up on the product side of the arrow. What we also see here is sort of the hallmark of a nuclear reaction, which is there is no conservation of elements. So unlike in a chemical reaction, where we balance the equation by putting coefficients in front, because we do have conservation of the elements, because those guys only involve electrons. Here, what we are really changing is everybody in the nucleus, so protons to neutrons, neutrons to protons. And as we change the number of protons, we are changing what the element is. So there is no conservation sort of elements in nuclear chemistry. And it is the proton or the atomic number, right, that determines what element you're talking about. As the number of protons changes, so does the element as well. Any questions on that there? All right, so why don't you give this a go. PO212 decays by alpha emission. Write the balanced nuclear equation for this decay process. And again, if you have a periodic table, it's probably going to be super helpful. If you have one, you might want to pull it out. Help you for some of these things. Take a look at this. So first off, we are starting with 212 PO here. 212 is the mass number. We could go to the periodic table to fill in our atomic number. If you do, it looks like it's an 84 there. It is going to decay by alpha emission. So again, that alpha emission means that on the right-hand side, our product side, I should have my alpha particle, which again, you could write this way or this way, whichever one you prefer, is all good. And that means we are going to really be missing one more thing here to sort of complete out the equation. Once again, I personally will start with the atomic number because that's going to help me go to the periodic table and find what I need. I obviously have 84 on the left-hand side. I got 2 on the other side. That means if I subtract that, my missing atomic number is 82. And once again, I could simply go to the periodic table and find number 82, which is our good friend lead. And to truly finish it out here, we're going to finish our mass number. So once again, on the left-hand side, I got 212. Right-hand side, I got 4. And if I subtract that, that gives me a mass number of 208. If I could write the 8 there, 208. And that means that this would be our balance.